Good day, I'm Maile Matsiba. Welcome back to our channel. Today we're going to be continuing with the introduction of section 2 concepts. So we're going to be doing part 2 of it. And in this part we're going to be focusing on concentration as it has different aspects. So the very first one that I want us to talk about is mass per unit volume. Now in mass per unit volume, it's actually mass of solute all over volume of solution. Now this solution includes both solute plus solvent. Our solute would be what we dissolve, maybe salt or water, salt or sugar or whatever compound that might be dissolved, and our solvent would be like water, for instance, or any other liquid that we might use to dissolve anything. So that is actually the mass per unit volume of solution. So it's very much important to understand that in mass per unit volume of, okay, let me just highlight here, of solution, is that the volume of the solution is the volume of both the solute and the solvent. Now the second one is mass per unit volume of solvent. This one then becomes mass of solute all over mass of solvent. Remember, in the first part we have the mass of the solute, volume here, Remember, in the first part we have the mass of the solute, which is your salt or sugar, over the volume of the solution, and the solution being both the volume of the solute, which is what we're dissolving, and the solvent, what we're dissolving in. Now in this case we have the mass of the solute with your typical sugar or salt, and over the volume only of the solvent, maybe water or anything we can actually use. So that is actually the mass per unit volume of solvent. It's very much important to notice the difference in these two. Now the third becomes parts per million. Parts per million. So parts per million is always expressed in mass. Okay, let me just, most of the, or should I say, it's always expressed in mass. And now one thing I need to highlight is that mass, or rather parts per million, most of the time it works with very low concentrations. Maybe you have your like 0.000004 grams per kilogram, so it's a very low ratio of the grams. So instead of just putting it as 0.000 and many zeros and whatever number, you could actually express it as parts per million. So it becomes very much handy when you have very low concentrations. So now the fourth one becomes molarity. Now molarity becomes gram mole, let me say gram mole solid all over liter of solution. Now molarity is actually expressed as gram mole solid, or what has been dissolved, all over the liter of the solution. It's almost like the first one especially, but this time around here you have the gram moles instead of like your typical mass. And also our solution is actually expressed per liter. it's important to understand that in the first one we don't really have like your restricted volume, like unit, not really units, but the capacity of the volume here, if I were to put it that way. But in this case, we have gram moles per specifically liter solution. So which means after you calculate the gram moles, we express them per liter. So that is our molarity. And now number E becomes, oh, let's just, yeah, normality. Now, normality is grams equivalent per liter solution. So gram equivalence per liter solution is almost like your gram moles per solid, gram moles solid per liter solution, and it's also expressed as liter, or rather per liter of the solution. So whatsoever that has been dissolved, the gram equivalence of what has been dissolved, and all over the liter of the solution. I guess I'm explaining it a little bit easier. And another one I want us to look at is your molality. Molality becomes gram mole per 1000 gram solvent. 1000 gram solvent is also 1 kilograms, just to highlight that. So this one is the gram moles of whatever that has been dissolved per kilogram or per 1000 grams of solvent. This solvent is not the solution, it's not like this one. It's always important to understand that in this case here there was a solution, though it's a liter, and now we have 100 grams of the solvent. Either the water, most of the time the water, or anything you can ever use, as long as it's something that you dissolve in something in it. So yeah, that's what is it. And another one that I want us to talk about is mass fraction. Mass fraction is actually how do I explain it easily? It's actually, well, let me just say it's mass of a specific. This mass fraction most of the time works when you have different compounds or different elements in one container, and and you have the mass of one compound, or rather you have the mass of all the compounds, and then you need the fraction or the percentage. It's not really percentage, but I just want to use the word percentage to make it much more easier in explanation. Then you have, let's say you have, or let me, in practical terms, let's say you have 3 compounds and you all know their masses. So what you do is you actually, if you want the mass fraction of a particular, of a specific element or compound in that mixture, you calculate, you will then just express, you will then just say the mass of that particular compound all over the total mass. So this one is also not so difficult. Like for instance, if I were to make it a little bit more practical, let's say you have nitrogen plus oxygen plus CO2, right? Let's say these are the 3 that you're working with, right? And you know both their masses. So if you have the mass of this one and this one and this one, now the mass fraction N2 would be mass N2 all over mass of N2 plus O2 plus CO2. That is basically the mass fraction. So it's nothing really complicated in itself. It's something that I believe it's easy to understand. And this I just had to go through them in paraphrasing, but I believe as we're going to be diving much more deeper into section 2, they're going to be much more clearer when we use them in practical terms, like solving questions that specifically works with them. So yeah, thank you for your time again, and meet you again in our next video.